Okay, so we're back with us now. So we're talking about the Mclafferty rearrangement. I think I've got the question on the wrong one. Yeah, we're at this one. So the Mclafferty rearrangement is observed in mass spectrometry during fragmentation of carbonyl compounds. It is an electron rearrangement that occurs when you have a gamma hydrogen. So if we locate the gamma hydrogen in this one here, so we've got the main carbon, alpha, beta, gamma. So we're talking about this gamma hydrogen. On a ketone, well, that's the gamma hydrogen, that's the gamma carbon, and then gamma hydrogen on a ketone or aldehyde oxygen, yielding an alkene or enol. So just to run off the bat, so just to be very simple, we know that that's our alkene, which is there because you've got carbon and a carbon, double bond is an alkene, and an enol radical. Off the bat, I wouldn't know what an enol radical would be, but something weird over here, so I'm going to assume that's it because we know that basic chemistry, we know our alkene. The rearrangement is seen during mass spectrometry where compounds are separated in accordance with their mass per charge, M over Z. So just remembering we need to understand that. So mass per charge, meaning mass over charge. So Z is denoted, the charge is denoted by the Z. Right. So the question states what is the starting reactant of the following products? So if we just try and understand that we have products here, so that would be on the right side of our equation, which is on this side, and on the left side we'd have our reactants, and there'd be like a double-headed arrow, meaning back or forth. So basically, just trying to briefly understand that if we don't start with our hydrogens, because our hydrogens are always a bit more complex to sort of count, we can just start with our, we'll just quickly have a look and make sure, because obviously the double bonded oxygen to a carbon is quite an easy one to sort of differentiate, but they all have the double bonded carbon, double bonded to oxygen, so I can't use that to help me, but I could see that if we look here, so the following products, so if we move to carbons, we can see there's 1, 2, 3, 4, 5, 6 carbons, so the only one here that has 6 carbons, roughly assuming that nothing else jumped in and there was no sort of nothing added, like an intermediate added to the equation when it from reactant to product. We're just looking at carbon. So 1, 2, 3, 4, 5, 6. That sounds good to me, but we'll just count the rest. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. And 1, 2, 3, 4. So the only one with 6 carbons, which was the amount of carbons that added up here, is number A, so that one's correct. So moving on to the next one we've already gone through the stem earlier, but we'll just quickly, roughly, if you want to have a quick read of that one. So what are they wanting us to do? So we'll just quickly look at the responses here. So you've still got the same crap here. So double bonded oxygen to a carbon is consistent. Which of the following compounds cannot take part in the Mclafferty rearrangement? So if we look here, we can remember that they were talking about the gamma hydrogen, which is there, so the gamma carbon. So the way I did this was just count to make sure, to see which one, and we're talking about which of the following cannot, so the false one. So 3 of them should be true, 1 of them will be false. So basically, we have a gamma hydrogen, so I'm going to count the carbons and try and work out which one doesn't have that. So if we start with A, so we've got our main, and remember with chemistry nomenclature, the order of priority would be our number 1 primary carbon would be there. So then it would be the main carbon, and then it would be alpha, beta, gamma. Is that right? Alpha, beta, gamma. So that should be right because that would work because there is a hydrogen on our gamma attached to our gamma carbon, meaning that there's 3 of them that we could use. So that sounds right to me. The next one is alpha, beta, gamma. Is it alpha? So our main carbon there. So alpha, beta, gamma. So there is a gamma hydrogen here because that's our gamma carbon. So that one looks right too. So then this one, main carbon, alpha, beta, gamma, gamma carbon, gamma hydrogen. That looks good. This one, main carbon, alpha, beta. There's no gamma carbon, and thus there's no gamma hydrogen. So it would not be able to take part in the Mclafferty rearrangement. Again, main carbon, alpha, beta. So there's just no way, because there's no gamma. So that's a quick way we can look for that one. Alrighty, so this one's a little bit more confusing, but it shouldn't be too bad to get your head around it. So basically, I'll just confirm that we're in the right one here, and yes, we are, all good. So basically, we're still talking about the Mclafferty rearrangement. So the question's asking, for the following rearrangement, which carbon in the products comes from the carbon denoted by the asterisk? So the asterisk is there, as we can see there, and then products, so we're on the right-hand side, as I said, products to the right, reactants to the left. So we're trying to follow this carbon here, and which carbon in the product comes from the carbon denoted in the asterisk. So when that changes from there, where is it actually placed in there? Is either A, B, C, or D? So for that one, it sort of requires a little bit more understanding about what's actually going on with the whole thing, and like the actual where everything goes and the spatial sort of awareness about what happens in this one. So basically, I got this one wrong, as you can see here, but as I know, we've got alpha, beta, and gamma hydrogen. So just knowing this equation will help. Whether this comes up in the GAMSA, I don't know, but it'll help sort of to understand it, hopefully. So, and just understanding what happens in a quick roundabout way is always helpful. So basically, what's happening here is, and I mean, I don't really understand how they could actually expect you to understand where bonds break and where they become like back together and stuff like that. But apparently you should know how to do that. So whatever. All right. So basically, in this situation, we have the alpha beta bond breaking to form the alkene, basically, and this pushes up to the right. Pushes up to the left, which I'll show on the whiteboard in a second. So that becomes your alkene there. So this shit all stays the same, and that's there. And basically, what pisses me off is when they just put like if you don't understand chemistry that well, which I don't particularly understand it that well, but they've only got one hydrogen there. But really, if we just use common sense right now, like alpha, beta, gamma, the gamma carbon has to have two more hydrogens attached to it, because it would be breaking the octet rule if it's not bonded to four things. Carbon needs to be bonded to four things, but here they've only sort of shown in the diagram that it's attached to one hydrogen and one other carbon, which would mean it's only bonded to two things, but it has to have another couple of bonds. It has to be CH3, really. But anyway, because that was in the last one, I'll go back quickly. See how it's like CH3? You can see that alpha, beta, gamma, it has three, but so that one shows it, but this one just shows that, are we in the right one? No, we're not. Well, that's not fun. I just lost it. Mclafferty, I'll try and find back where we are. No, we've already answered that question. So we're back to this one, sorry about that one. So yeah, it would help if they had the three, but I'll show you that in the whiteboard now. So we'll change to our next scene. So I'll just try and straighten that one out. Mclafferty rearrangement. Sorry if it's a little bit difficult to see. Oh, you're not making it easy on me, are you? Just trying to straighten this one up for us so we can actually see what I'm trying to say. Alright, all good, so that will do. So basically for this one, we have, that's what I've drawn here with the, if you can see as close as possible, but the hidden carbons does sort of help you understand it a bit better. So careful what colour I'm going to write with. So I've written my hidden carbons because we knew from the gamma carbon there that it had to be joined to three. So there's actually three. So basically what I'll do is I've also got my two lone pairs, and that becomes one lone pair over there with a positive charge as well. So basically in this situation here, we've got these two. So it's, again, the question's asking us with the gamma carbon, where does that fall in our products? because we've got here, it could be that one, that one, that one, or that one. I think I chose that one just as a guess, but that was completely wrong. So basically, if we understand what's happening in the reaction, it makes it a little bit more easier to understand. So what I want to explain is that what happens here is the alpha beta bond breaks. So because this shit all stays the same, so I'll even draw this in a circle. This shit doesn't change because that's over there, and only things that happen is shit gets added onto it. And as we can see over here, our hydrogen gets added onto it. So this hydrogen, and I've drawn that hydrogen in the specific color so we can identify that this actually joins to that, but we'll split it over. So I'll draw an arrow, and that's that one, that hydrogen's added to the oxygen over there. And there's a reason why that happens in a second. We'll understand that one. So basically, the other thing that happens here is that this bond's broken. So this bond, and I'll draw that, becomes there, and I'll have a double-headed arrow, so we know that that becomes a double bond, as you can see there. So although that's over there, I'll just draw it below because there's a little bit of a trick that they do with you. So basically, what happens is we've got our, and then we've got our two. I always forget how to draw the gamma sign. There we go, I did it. Beta. So our beta carbon and gamma carbon will change now, but let's just to keep understanding where we're at, and I'll keep drawing that because that's essentially this one. So there's essentially a carbon at this side and a carbon at that side. So, but what we need to understand is that you've got your carbon double bonded, but we need to can't break the the octet rule. So what we need is to have two hydrogens still there. So unfortunately, it doesn't draw it as well, but I'll keep going to help us understand. So I'm going to go, instead of drawing that, but I can do that. I'll go H2. So if that makes any sense, which is essentially H2 is two hydrogens, which is the hidden one. So it needs to be a bit kinked, actually, and I'll draw that just so we can keep consistent to try and understand what they're wanting us to do. So it's like this, H2. So basically, that's how we'll understand, and then what they've done is flipped it around, and it's become here. So that's our kink there, and unfortunately, it would have been helpful if they just drew it a little bit clearer and helped us out a bit better, but they haven't. But that's right, this is GAMSAT, we know that. So that's our beta carbon is there, our gamma carbon is there, and these are just our H2s. Now, I mean, remember that's not a C for carbon, that's a C for an answer. But I always get confused here where I think that was there a carbon there or not. So that's just something you have to get more familiar with as time goes on. But there is no carbon there. It's actually two hydrogens, but they just make it there to make it a little bit more challenging for you. So we can see here that that's actually our, I'll draw them in the same color. This is our hidden H2s. That's our H2s, H and H. So I chose C, which is incorrect, and as I said, our asterisk would be on B, I'm pretty sure, no, our asterisk should be on that one, yeah. So that's our asterisk, which is equivalent to our gamma hydrogen, which is equivalent to our gamma and gamma carbon and beta carbon. So yeah, that's sort of not too hard to understand, but I mean, I struggled a lot with this one just because of the time constraints as well, but actually knowing how to understand what's going on, where the bonds break, it's a bit challenging at this level for me, but you can work it out with a little bit of understanding from it, and hopefully that makes sense. So just as we can see here, the answer was C. Oh, the answer was not C, sorry, the answer was B. I chose C, which was wrong because that was again our hydrogens, but the answer was B, which is where our gamma, but it was just flipped around, that double bond broke. I mean, that single bond broke, the alpha beta bond broke, and it joined to make an alkene, and thus our gamma carbon remained there, and that's our gamma carbon. So yeah, if we can try and understand that, but it takes a bit of a while to get used to. Okay, so I've got the next question here, back to the Mclafferty rearrangement. So what would happen to the mass spectra if a residual carbon from the alkene is added onto the enol radical. So with this question here, it's a bit of a fun one. So when I say fun, I mean a little bit difficult to understand. But basically, so they're talking about residual carbon from the alkene. So let's just say like another carbon, that carbon is added to the enol radical. So we need to be able to understand. I'm just going to check, make sure we're in the right screen, which we're not. So basically, yeah, we're talking about the residual carbon, which is just here, residual carbon from the alkene, is added on to the enol radical, the weird one here. So I got this one right. The peak will shift to the right. That was an absolute guess because I had no idea what they were talking about. The shift will peak depend on the type of radical formed. The peak will shift to the left. The peak will not be shifted with this change. So I didn't think it would be that one. So I thought it would either be an A or B. Usually that's a good way to go because it's either going to shift one way or the next. So I was sort of able to probably, in hindsight, score it to A or C, which is always a good option, especially during time constraints, as we know this is what this is. So basically, what would happen to the mass spectra? So we're talking about mass spectra, which is this diagram right here. Just loading that one. So I don't really understand the abundance part, but that's the truth here. But so MZ, so that's about our mass per charge in accordance. So that's mass spectra is talking about mass per charge, which is this line here. So basically, we need to be able to understand. Even if you couldn't understand it, it's still fine to do this. But basically, the radical there, which is I believe is the plus charge there. So I can't, even if I could add a free carbon floating around, I can't add it to here to remove that charge because oxygen can only have 3 bonds at max, and that's with its retaining a lone pair and a positive charge. That's easy to see on this here, as you can see. So oxygen can have a max of 3 bonds, which is a positive formal charge, 3 bonds plus 1 lone pair, which is what we have. There is no way we could have a fourth, like I couldn't add another, like use that charge to make it another bond to carbon because that's just not the way oxygen won't tolerate that. But this one's always good to have. So negative formal charge, 1 bond, 3 lone pairs, or that's what we had at the start, which is the double bond with the 2 lone pairs, which was in the beginning double bond with 2 lone pairs. So just always remember, it's easy to remember, but becoming familiar with how much bonds that can connect to like those main atoms is really important. So basically that sort of, even if I could do it, I don't even know if you could do this, but if I added like another carbon here to that part of it, maybe, I don't know. As I said, chemistry is not my strong suit. I'm not, that great at it, but I just, knowing that I can't just remove the positive is a helpful one. So thus the charge is still going to be a positive charge, a positive net charge of the compound right here. So if I know that the Z, this is what they're denoting, charge equals Z, which is written here, won't change. The only thing that would change is the mass of the compound, which would be adding another carbon. So I'll chuck it on here and have a look. So I've written it up here for what actually we're talking about. So if I have a carbon added to the enol radical, which is there, so mass charge equals, this is the number, like 0.5. So mass over Z equals, let's just say, for example, it was 5/10. So just to be simple, obviously it's not 5/10, but still it's always good to simplify when it comes to this stuff. So a 5 units of whatever is a mass, and then 10 charge, the answer would be 0.5, and that would be depicted on the x-axis on that graph, which is shown in the stem, so a number of 0.5. Now, if we have a charge stays the same on this one as 10 and 10, but our mass doubles, we have a mass over charge ratio of 1, meaning if we look back on that charge, the x-axis, this is what that means, these numbers are there, so it would push it to the right because that number would get bigger, as you can see, and the opposite's true in the opposite direction. I think if we had the mass stay the same and the charge get smaller, it would go to a smaller number, and thus it would be a shift to the left. So, but also being aware to know that adding that carbon added to the enol radical is not going to change the net charge. is a bit difficult to know, but I think it's just a wild guess at this point, and that's what it was for me. But yeah, that would help. So just knowing the sort of how the calculation works is pretty helpful. And we can see here that, yeah, it peaked to the right. So that was my number when I made on the whiteboard. It says that, yeah, so at the moment, before the carbon was added, it was 0.5, for example, and then we we increased the charge, so increased the numerator, and retained the same value in the denominator, pushes the charge up, which pushes the whole thing to the right, which is like the ratio to the right, which is up here. So hopefully that sort of made some sort of sense. But again, you just have to sort of guess with it and hope that you knew that the net charge would still remain the same as +1, and then see what that does. So with half of it, you can still kind of get to the answer. Alrighty, so our next question is, just off the bat, I got this one wrong, but and that's because I didn't understand resonance that well at the time. But basically, the products of Mclafferty rearrangement can undergo resonance stabilization. How would this impact the mass spectrometry peaks? Right, so understanding the resonance is a bit of a funny one, but basically what I'm talking about is it's about kicking the electron pairs around and then changing the sort of bonds, but you still retain the overall charge. The overall net formal charge still stays the same, I'm pretty sure. So that sort of means that we're not talking about an alkene because there's no bullshit there, like weird stuff, which is the lone pair and the plus charge. So all it means is changing things around to, just make sure, yeah. So changing those double bonds, moving them down or up, and moving stuff around to sort of get stability. But yeah, so basically, Joe Chem does it a lot better than I can, which is this video here. So he's really good at explaining about resonance, and I suggest you all watch that. And he talks about the rules and stuff like that. So I watched this video, and it sort of made it a little bit more clear about what's going on. And yeah, in one of his options, he talks about that sort of stuff. So basically, the answer is all resonance structures will have the same peak. And that's because it's only changing the double bonds around, but the charges still stay the same. So off the bat, you should be able to know that. And that they're only talking about this, and the alkene is not. They're not talking about that because it doesn't have the charges or anything like that. So resonance is basically to try and get more stability and by moving stuff around. So yeah, I've talked about it here in their understanding resonance example shown still have mass, same charge. So they still have the same mass and charge. That never changes. As such, we'll expect the resonance structures to have the same peak. This is because mass and charge units will not change. This makes B correct in AC. So you can see that they've just changed the positive charge, moves down and eventually comes to there, but it started up there. So by just changing bonds around, you can sort of get there. And yeah, resonance structures will have the same peak. So yeah, but doing some extra learning about resonance will definitely help. So all good. I think that's the last question. We'll just confirm. Yeah. Thank you very much.